Before I do the last two tests, which is the ratio and the root test, I want to talk to you about the alternating series one more time. There is one other thing about alternating series I haven't told you, and that is that there's something called conditionally convergent and something called absolutely convergent. This series is conditionally convergent. And the reason is because if I use the alternating series test on this particular problem, I realize that each term is less than the one before it. And I also know that the limit as I approach infinity of 1 over n without the negatives is 0. So it converges with the negatives by the alternating series test. However, the series without the negatives, just the 1 over n, that diverges because of the p series, and p is 1. Well, because the series without the negatives diverge and the series with the negative converge, that makes it conditionally convergent. The actual rule is that the sum converges, but when you take the absolute value of the sum, and we actually take the absolute value before we take the sum, like this right here, but it diverges. So you just have to check and see, do the positives converge and do the positives and the negatives converge. Absolutely convergent mean that an converges, and when I take the absolute value of it, meaning get rid of the negatives, it also converges. So an example of this one, if I have 3 over n to the third times negative 1 to the n plus 1. If I do alternating series test, I know that the limit of 3 over n to the third as I approach infinity is 0. I also know that every term is less than the one before it, so it converges by the alternating series test with the negatives. Now if I take away the negatives, we have 3 over n to the third. That converges by the p series. So it converges with the negatives and it converges without the negatives. That makes it absolutely convergent. There'll be one try problem related to that. Basically, I'm going to ask you if it's absolutely convergent or conditionally convergent. And usually it's only applied to alternating series. The other thing that I wanted to show you about alternating series, I'm just going to kind of show you, we won't do many problems with it, but there's something called the accuracy or the error, and it only applies to alternating series. Basically what it says is that if you have an alternating series that is convergent, then the remainder is equal to the large sum, the sum of the whole thing, minus the sum up to a certain term, that the remainder is less than or equal to the next term. In words, they say this: the error is at most the size of the neglected term, which basically just means the next one. So let me give you an example of that. First of all, on these problems, you should always prove that it converges, and it does, because each term is less than the one before it. If I wrote out the terms, I could see that. Also, the limit of u approach infinity of 1 over n without the negatives does equal 0. So we do have a converging alternating series. Let's say that we wanted to find the sum up to the third term. Well, the sum up to the third term is 1, because you plug in a 1. Now plug in a 2, you get negative a half. Plug in a 3, you get a third. And we could figure that out. That's the sum of the up to the third term. Well, what we're asking here in this kind of theorem that we're talking about is I want to know how much we're off. I want to know. So I'm trying to figure out how much we're off. Like how much, if I found the sum of the whole entire series and I just find out this sum, I want to know kind of what the error would be. So what this rule says is that if I wanted to find the error, then I find the next term, which in this case would be, you always take the absolute value of it, because if you'll notice here, we took the absolute value and the absolute value of the remainder. So the error is at most 1/4, which means if I found the sum of the whole thing, that the sum of the whole thing minus the sum of the third term would be less than or equal to 1/4. So we're only off by 0.25. Now, the problem would have to tell you like how many to find the sum of. So if it said, well, let's find the sum up to the fourth term. Well, that'd be 1 minus a half plus a third minus a fourth. If we wanted to find the error here, then the sum minus the sum up to the fourth term would be less than or equal to the fifth term. So I plug a 5 in there, I get 1/5, so it would be less than or equal to 1/5. And the more terms that you find, the sum will be off by that much less. This particular kind of problem showed up on the AP test last year, and I didn't talk about it at all, so I wanted to make sure that I showed you what was going on. Now, for the actual other test that I wanted to talk to you about, that's the ratio and the root test. Basically, they're very, very similar. The restrictions are very, very similar. So first, let's talk about the ratio test. Ratio indicates a fraction, so usually we're talking about fractions, and we're going to create more fractions. What it says is that the series that you're talking about has to be non-zero, which means no zeros in the problem, as far as what the series would be. Most of the time, that's a very quick one to check. And AN converges if, when you find the limit as you approach infinity, if you take the next term and divide it by the previous term, if you do the absolute value of it, is less than 1. So if you get something less than 1 when you do this thing right here, it converges. It diverges if same limit is greater than 1 or infinity. I consider greater than 1 to be infinity. I consider infinity to be greater than 1, so it makes sense that that would fit that description. And then lastly, if you do the same thing, but instead of getting a number greater than 1 or a number less than 1, if you get 1, that the test is inconclusive, meaning you got to do another test and it will help you. Most of the time that will not happen. Most of the time it's either going to converge or diverge because you'll get a number greater than 1 or a number less than 1. So let's look at some examples for the ratio test. So here we have a series. If I'm going to use the ratio test, the very first thing I'm going to do is I'm going to plug n plus 1 in all the n places. So I have 4 to the n plus 1 over n plus 1 factorial. And I'm going to divide it by 4 to the n over n factorial. So I'm just going to go ahead and flip it and change it. And so I want to know the limit as n approaches infinity of that. Alright, so this is where manipulation comes into play a little bit. You got to think about what to cancel and what you can't cancel. If you have 4 to the n plus 1 over 4 to the n, you can subtract those. 4 to the n plus 1 minus n. So on the top you end up with 4. Because that's 4 to the 1. Now, the n factorial and the n plus 1 factorial. Okay, n factorial is like n times the previous term, which would be n minus 1, because that's 1 less, times n minus 2, and then it just keeps going down. N plus 1 factorial would be n plus 1 times the 1 below that, so subtract 1, you would get n. The 1 below that, n minus 1, 1 below that, and then it keeps going. Well, because we're dividing here, notice all of these cancel except for this n plus 1. So this limit equals 4 over n plus 1. Alright, we're trying to approach infinity. So we have 4 over infinity. That means that this equals 0. So with the ratio test, I got 0. The ratio test says that if you get a number less than 1, that the series you started up with converges. So this series that I started with converges by the ratio test, because this number is less than 1. Alright, if I'm going to do this by the ratio test, I'm going to start off by plugging in an n plus 1 in all the n places. When I plug an n plus 1 up there, that's an n plus 2. And then I divide it by the original, which means I flip the original. Alrighty, n plus 1 and n, that just stays. Alright, 3 to the n and 3 to the n plus 1. If I subtract exponents, I end up with a 3 on the bottom. 2 to the n plus 2, 2 to the n plus 1. Subtract those exponents again. End up with a 2 on the top. Alright, we're trying to find the limit as n approaches infinity. And if you'll look at this, top and bottom have the same degree, except that they're multiplied by the 2 and the 3. So this limit is 2/3. Because we get 2/3, which is less than 1, then we can say the original problem converges by the ratio test. Alright, so here's another one. We're going to plug in n plus 1. Divided by that thing, so then I flip it. Alrighty, the 5 to the n's, subtract exponents, so I get a 5 on the top. The n squareds just stay. And now I'm trying to find the limit as n approaches infinity. Same degree top and bottom. I get 5, which is greater than 1. So the original series diverges by the ratio test. Alrighty, same thing again. Be an n plus 1 on the top. 2 to the n plus 1 over n plus 1 factorial. Flip it. Alright, that gives me a 2 on the top. This gives me an n plus 1 on the bottom, because this would be n minus 1, and so on. This would be n plus 1, n minus 1, and so on. And then the n plus 1 and the n stay. And if you'll notice, n plus 1s go away, so we get 2 over n. We're finding the limit as n approaches infinity. The top is less degree than the bottom, so we get 0, which is less than 1. So it converges by the ratio test. Alright, lastly, I want to show you the root test. Same conditions sort of apply as the ratio test, except you take the root of it instead of the ratio. So you take the nth root of a to the n. If it's less than 1, it converges. If you take the limit with the root of a to the n and you get infinity or greater than 0, then that diverges. And then it's inconclusive if you get 1. Just like the ratio test. We're on number 5. Most of the time, you'll know it's a root test if it's raised to a power, and this power is supposed to be n, not 2. And if you see it raised to the power, it's probably using the ratio test. So what you do is we try to find the limit as n approaches infinity of the nth root of n plus 1 over 2n plus 3 to the n. Now if you take the nth root of something to the n, you end up with n plus 1 over 2n plus 3. Now find the limit as you approach infinity. That equals a half, which is less than 1. So it converges by the root test. This is not a common test, but it's an easy test to tell because something is raised to a power usually. And although this one is separated on top and bottom with the 4n and the n, it's still all raised to a power. So I'm going to take the limit as n approaches infinity. And I'm going to take the nth root of 2 to the 4n over n to the n. The nth root on the top, that'll get rid of the n, so I get a 16 because 2 to the 4th is 16. The nth root of n to the n will just give you an n on the bottom. That equals 0, which is less than 1 because of the limit. And so it converges by the root test. Alright, here's your try problems. On number 4, I want to know if it conditionally converges or absolutely converges. It's like the very first problems that we did where it was alternating series and then you had to figure out if it was conditional or absolute. The first two will be the ratio test. The last one will be the root test. The way I can tell that number 3 is the root test is because it's all raised to a power. Now, number 1 and number 2, there are things raised to powers, but it's not all of it, so that's the reason it's not the root test.